Hello everyone, my name is Ali Fakih from Université de Haute, Alsace. So I'm gonna present to you my work that I've done with Frederic Cordier and Yvan Maillot, which is entitled Piecewise Reconstruction of 3D Euler Spirals from Planar Polygonal Curves. As an overview of this presentation, I will start by talking about the motivation that led us to work on the idea of the 3D reconstruction. Then I will talk about the literature review by showing some previous work that have things in common with our work. After that, I will talk about our work, which is the 3D reconstruction of Euler spiral, and I will go into the details to explain how we did our approach, starting from the dataset creation to the curve segmentation algorithm, then how we dealt with connecting the segment, and finally the post-processing smoothing of the curve. After that, I will show you the result of our reconstruction, and I will end up this presentation by drawing a conclusion and speaking about a possible future work. So, firstly, the 3D reconstruction is a technique that involves creating a 3D representation of a three-dimensional model. So, as a motivation of our work, the 3D reconstruction is one of the most important techniques in computer graphics. Also, it's used by many industries, such as modeling virtual human for video games, special effects for cinema, industrial design, virtual reality, etc. For instance, here's some example of the use of the 3D reconstruction in video games. So here, from this figure on the left, they were able to do its reconstruction in 3D, as you can see in the figure at the right, using this work. Sorry. Here also some example of the use of the 3D reconstruction in the industrial design. If we continue, now if we will speak about our work, we can say that our work focuses in the reconstruction of a specific family of curves, which is the Euler spiral. As a motivation of why we chose to work on the Euler spiral, we can say that normally we as a human being, if we see a pattern whose curvature involves linearly, it's somehow easy to imagine its shape in 3D. Also, the Euler spiral curve is an eidetic curve, and part of the Euler spiral exists in nature. In addition to the previous reasons, from the technical side, the 3D Euler spiral satisfies the properties of eye-pleasing curves, such as invariance to similarity transformation, the translation, the rotation, and the scaling. Also, the symmetry, extensibility, smoothness, and roundness. And most importantly, having a curvature and torsion increasing linearly with curve length. Beside the previous properties, some researchers used the Euler spiral as a good solution for shape completion. As we can see here in this figure, they used parts of the Euler spiral in order to complete the shape of this projected object. And you can see also here the same example of using the Euler spiral in order to complete some shapes. And you can refer to this work if you need any more information about it. So, in the literature review, we didn't find many articles that work on the same approach that we are working on. But I will mention some of the previous work that have something in common with our approach. So, firstly, there is the reconstruction of ellipses from their orthogonal projection. And as its name title said, it's a reconstruction of ellipses from their orthogonal projection. The idea behind it is to search for the ellipse whose orthogonal projection fits best with the input curve. And to do so, they used some special properties of ellipse with some optimization technique in order to find the ellipse parameters. Then there is the article whose title is Learning 3D Face Reconstruction from a Single Sketch, where here they try to create a 3D face reconstruction by firstly creating the sketches from the original image, then creating the 3D reconstruction using some existing models of machine learning. But there is, as they said also, as they described also, there are many existing methods to reconstruct 3D face model from photo, such as 3D based method, and so on. Here, there is the article Interactive Sketch-Based Normal Map Generation with Deep Neural Network. So here they tried to create a normal map of this input sketches, and they used the GAN algorithm to achieve their goal. And there is this work also, which is a very interesting work, which is the 3D Euler spiral for 3D curve completion. And the idea behind it is that having a two discontinued point, they try to find part of the 3D Euler spiral that can create the link between these 2 points. And finally, the work most closely related to ours is this one, which is the sketching clothoid splines using shortest path. In this work, they also reconstructed the clothoid spline in a piecewise manner from polygonal curve and achieved very good results. However, their method is limited to 2D clothoid and cannot be used for 3D reconstruction, as opposite to our method, which produced a piecewise 3D Euler spiral that fits a planar polygonal curve. So, coming back to our work, the ultimate goal of our approach is that when we will have an input curve which is a part of an Euler spiral like this red one, we should be able to do one of its reconstruction into 3D. So usually the common approaches for curve matching are to compute the curve parameters using an optimization algorithm. But in our case, these approaches doesn't work because firstly, the analytic equation to compute the point on the Euler spiral doesn't exist. So it's like there is no analytic solution, and also computing point on the curve requires a lot of computation time. So instead of doing the typical curve matching that will take a lot of time, we thought of creating a dataset that contains different shape and pieces of Euler spiral. And we can use this dataset in order to do the matching. And as you can see, here, the pieces are small because if we want to think about a full matching of the curve, this would be hard and complicated because we cannot know how long the curve could be. So instead of the full matching, we divided the curve into pieces and we applied the matching piece by piece, as you can see here. So at some point, we can say that our approach is similar to curve signature, where its signature is based on the point coordination. So the next step is that for each piece of the input curve, we have to search for its most closest match in the dataset. As you can see here in the figure, we firstly split the curve into 4 pieces. Then for each piece, we have to look for the data set for the best match. And from the best match, we can get its reconstruction to 3D. So we can apply that in order to formulate the reconstructed Euler spiral. If we look here, if we assemble the pieces that we get from the previous step, at the last step, we can get the reconstructed Euler spiral. So, as an overview of our approach, firstly, we created a dataset that logically should cover any piece of Euler spiral. Secondly, when we have to deal with any input curve in order to find its 3D reconstruction, we should split the input curve into pieces, then finding the matching for each piece, which means looking for its closest match in our dataset. Thirdly, we have the pieces assembling, when we will have to assemble the pieces that we got from the previous step, and this assembling will be based on the smooth continuity of tangent, curvature, and torsion between each two consecutive points. Now I'll explain each one of these three steps. So the first step is the dataset creation, where in order to create our dataset, which is composed of short segment of the 3D Euler spiral, we follow the approach introduced in the articles that I showed you before about the completion of the Euler spiral, where they define the 3D Euler spiral as the curve that should minimize the sum of square variation of its curvature and torsion, therefore minimizing this integral. And by doing so, by applying this method, we were able to create like the pieces of the Euler spiral. So now if we want to think about how our data set should look, we have different parameters to think of, like the starting and the ending position of the curve, and finally, rotation angles. Furthermore, we have also to keep in mind that this data set should cover all possible pieces shapes, but at the same time, it should be as small as possible in order to make the needed time to apply our approach as quick as possible. So to achieve this goal, we applied like an approach which is the scaling and uniform sampling, and I'll explain each one of this part in the next slide. So starting with the starting point, in order to ensure that our dataset adequately covers the diverse range of input polygonal curve, we make the starting point parameter of the dataset segment to have different values along the spiral, Euler spiral. To achieve this, we uniformly sample the starting point parameter along the curve in the interval SSA and SSB, as you can see here. By doing so, we ensure that our dataset includes segments whose curvature changes from negative to positive value. And also, we selected SSB as the upper parameter limit, since as more than this point, the curve exhibits a repeating pattern and is getting similar to a circular shape beyond this point. Now, concerning the length of the segment, we choose to make the segment short because long segment would require a larger dataset to cover all possible input curve. We achieve this by limiting the tangent angle difference between the starting point and the ending point to a value within the range between pi and pi over 4. Therefore, the ending point of this segment that starts from here should be between this point and this point. Now, about the rotation. To represent all possible projection of the 3D Euler spiral segment, we apply rotation alongside x, y, z axis for each segment of the dataset. As you can see here, here is the matrix whose contain the coordination of the point of the dataset, and here the rotation matrices. And we uniformly sampled the values of the rotation in the interval between 0 and 2 pi. Now, if we think our dataset is composed of 3D Euler spiral segments, after splitting the input polygonal curve into segments, for each input segment, we look for its closest match Euler spiral in the dataset. But since the input curve in 2D, the matched segment should be in 2D also. To achieve this, we orthogonally projected our dataset segment onto the XY plane. So to establish a systematic search approach, we take advantage of the 3D Euler spiral property, which is the invariance to similarity transformation. And we apply a uniform scaling for all segments in our dataset, making all having the same length while preserving their original aspect ratio. And by doing so, we remove the scaling factor from our dataset. So as we can see here, we have two pieces that have the exact same shape in 2D and 3D, but with different numerical lengths. So the idea is that when we will have to deal with any curve in our approach, we apply uniform scaling which mean here in this example making these two pieces having the same length, having exactly the same size, we can say. So the next step is like when we have to search for the closest matched segment from each input curve segment is based on the 2D freshness distance between the input curve and the orthogonal projection of our dataset segment. To do so in a good way, we require both the input curve segment and the dataset segment to have the same number of points uniformly sampled at regular interval along the arc length. This ensures that the distance between any two consecutive points is equal in both, which enable a fair comparison. So, for instance, if we calculate the distance between the red and orange curve based on the sampling of these two curves, the result will not be as significant as if we calculate the distance based on this sampling here. Following the previous formalization of the data set, after finishing the sampling, we store our data set in KD3, which is a space partitioning data structure that enable a quick search for the any neighbor search. Now it comes to the curve segmentation. During the segmentation, our purpose is to decompose the curve into the smallest possible number of segments. This is to avoid any unnecessary computation time due to the handling more segments than needed. So at the end of the splitting, each segment of this input curve should have at least n matched segments from the data set such that the freshness distance between them and the input split segment is less than a threshold t, where n and t are user-specified parameters. So the splitting begins by taking the entire input curve as the first input segment. This segment is uniformly scaled and sampled in the same way we did for the data set. Then we search for its closest match Euler spiral segment in the data set stored, as I said, in KD3. If the number of matched segments is less than a threshold t exceeded a certain number n, then the splitting and matching process is done. Otherwise, we recursively split the segment into half, and then we take its first half and repeat the same process. As we can see here, this figure illustrates the recursive splitting to find the first segment of the input curve, and we repeat. Then here we find the first segment. Then we repeat the same approach to the remaining length of the segment. So as a result, for each piece, we get the n closest matching pieces using the Euclidean distance. Here in this figure, we have like 3 examples of the n in total result. So for the first piece, we have like 3 candidates, 3, 3, 3. So now it comes the problem of assembling. So as I was already saying, we have 3 pieces, and for each piece we have an option of matching. So now how to find the best pieces, the best assembling of pieces that suit the best with each other. For instance, if we choose like to take this one with this one in this order, we will have this 3D Euler spiral, which look very good. But let's suppose that we did like another way of assembling. We will get this one, which look like very terrible because we didn't choose the neighbor Euler spiral pieces that suit the best with each other. So we can like we can like say that as a result of the segmentation algorithm, for each segment of the input curve, we have n candidate from the data set. The final approximate Euler spiral reconstructed curve will be obtained by selecting one candidate per segment and connecting this selected candidate. In order to find this best connecting between the candidate of the input curve, the selection of any 2 candidates that follow each other should be based on the degree of smoothness continuity at their connecting point. As you can see here in this figure, we mean by degree of smoothness continuity, how smooth two candidates will link to each other. Based on the equation to measure the degree of smoothness, we define a loss function that calculates the square difference between the curvature coefficient, torsion coefficient, tangent, normal, at the ending point of the first curve and the starting point of the second curve. And by that, we can measure like how smooth two pieces could be assembled to each other. Therefore, the cost function, in order to find the best connecting of the pieces to form the reconstructed Euler spiral, we create a cost function which is a sum of the loss function between the pair of consecutive candidates. But to obtain the optimal 3D Euler spiral, it's necessary to identify the connectings that have the minimum value. So we thought of formulating this problem as a graph problem where the candidate represents the nodes and the loss function between each pair of consecutive candidates represent the edges, as you can see here. And to solve this problem, we applied Dijkstra algorithm by assigning all segments to a value 0, and then we search for the best path between any candidate of the first segment and any candidate of the last segment, and this will give us the best 3D reconstructed Euler spiral. After finding the best reconstruction, the connecting of the optimal set of candidates based on their position of their respective split segment in the input curve exhibits a gap between them, as shown for the first two matched segments in 1 and 2 here in the figure. So to address this issue, we apply a smoothing technique to the reconstructed piecewise Euler spiral. First, each segment of the piecewise Euler spiral is sampled into a polygonal curve. Next, we apply an uniform scaling for these polygonal curves in a way to make their extremity intersect at the same location, followed by resampling the entire reconstructed curve by interpolating the XYZ coordinate based on the cumulative Euclidean distance between successive points to ensure C0 continuity, as shown in figure 3 here. Regarding C1 continuity, it was already nearly preserved because of the loss function we already showed before. So, as an overview of the entire approach, starting from the splitting and matching step to the segment connecting and finally the curve smoothing to form the reconstructed curve is illustrated in this figure. Now, to evaluate the performance of our reconstructed algorithm, we did 3 experiments. In the first one, we generate 100 ground truth Euler spiral, all of which include an inflection point where the curvature and torsion change sign. In the second experiment, we generate 100 segments of Euler spiral, all of which have only a positive curvature and torsion. And we use the orthogonal projection of this 3D Euler spiral as an input to our method. Then we compare the reconstructed Euler spiral with the ground truth Euler spiral. While in the third experiment, we reconstruct an approximate piecewise 3D Euler spiral from hand-drawn polygonal curves. So, the result of the first experiment is presented in this figure, which show 4 reconstruction out of the 100 experiments that we did. As you can see, each reconstruction includes a comparison between the ground truth Euler spiral in blue and the ground truth Euler spiral in red and the reconstructed Euler spiral in green. Before applying the post-processing in ABVD and after applying the post-processing smoothing in E, F, G, and H. Yes, here the first one. In this figure, you can see the result of the second experiment, which showed the two reconstruction out of the 100 experiments that we did, and we have also the same result before applying the smoothing here and after applying the smoothing algorithm here. And you can see that both, and also we can see the curvature and torsion of both the ground truth and the reconstructed curve. the ground truth in red, the reconstructed curve in blue. To continue here, so here the result of the third experiment, which is the hand drawing curve. So starting from a hand drawing curve, we were able to do its reconstruction. We were able to find the 3D reconstruction of this curve that have an orthogonal projection very similar to the input polygonal curve. So regarding the result, as it's shown in all figures, our reconstruction produced visually eye-pleasing curve and quite similar result to the ground truth Euler spiral. Our reconstruction provides 3D curve with C0 and C1 continuity. Even G2 and G3 continuity can be considered acceptable since they are mainly continuous, except some peaks, as you can see, and the curvature and torsion occurring mainly at the joining point of the segment. Now, if we want to talk about the complexity of our algorithm, we use the KD3 to search for the matched segment from the dataset for each input curve. The complexity to search inside the KD3 is O log of Z, where Z is the number of nodes. We used also the Dijkstra algorithm, and the time complexity of the Dijkstra algorithm is O V plus E log V. Finally, the time required for each reconstruction varies depending on the length of the curve and the number of segmentation used to split it. On average, the reconstruction process takes around 50 seconds, with approximately 40 seconds spent on splitting the curve and searching for the matched curve, and 10 seconds spent to finding the best connecting of the segment. So, as a conclusion, we have presented a method to compute an approximate 3D Euler spiral such its orthogonal projection fits a planar polygonal curve. The effectiveness of our method has been demonstrated with a large number of input polygonal curves, and our reconstruction exhibit to have a continuity which make it possible to be used for 3D modeling and for generating motions and trajectories. As a future work, we are thinking to test our method against like some real-life application, and also we can extend our approach in order to be able to deal with more complicated shapes. Thank you for your attention.